Our next video here then is on the hyperbolic differential equations, this time being the wave equation, which I have written an example of here. U sub tt is equal to 4 times u sub xx. U of x comma 0 is equal to x times 1 minus x. U sub t of x comma 0 is equal to cosine of x. And u of 0 comma t is equal to u of 1 comma t, which is equal to 0. And from this, we need to separate our variables. So we have for this, we would have u of x comma t being equal to the x of x, that not being an x, times t of t. So here we are going to have the second derivative of t divided by t is going to be equal to then the value of, excuse me, I forgot a number here. T, the second derivative of t divided by 4t is going to be equal to the second derivative of x divided by x. And that is going to be equal to negative lambda. And so, based upon that, we then have when we separate these, we have our two equations. So t double prime over 4t is equal to negative lambda. That just means t double prime is equal t double prime plus 4 times t times lambda is equal to 0. And the other equation of x double prime over x is equal to negative lambda. That then implies that x double prime plus lambda x is equal to 0. And then based upon that, using this bottom set of initial conditions, we have, this would be u of 0 comma t, that being equal to, well, 0. That meaning that x of 0 times t of t, which implies that x of 0 is 0. Likewise, u of 1 comma t is equal to 0, means that x of 1 times t of t implies that x of 1 is equal to 0. So, based on that then, we have the solving this x equation here, we could obtain our eigenvalue lambda sub n is equal to n squared times pi squared. So this is our eigenvalue. The associated eigenfunction is going to be x sub n is equal to sine of n times pi times x. And this is where n is 1, 2, 3, and so on from that. So, based on this, replacing the lambda in this t function here with what we got, we have t double prime plus 4 times n squared times pi squared times t. That is supposed to be equal to 0. And solving this particular type of equation from differential equations will give us an equation of t is equal to c sub 1 times cosine of 2n pi t plus c sub 2 times sine of 2n pi t. So, because of that, we are going to have, and then again, we need to keep doing this for every single positive integer n that we calculate over here. This means that our equation t sub n of t, I'm going to introduce one small different variable, c sub n times cosine of 2n pi t plus d sub n times sine of 2n times pi times t. Again, this is for n. It's 1, 2, 3, and so on. Then, when we want to write what our actual equation is, we have u sub n of x comma t. And we can write this using our product solutions. This will be sine of n pi x times what we just got. So c sub n of times cosine of 2n pi times t plus d sub n times sine of 2n pi t. Again, n is 1, 2, 3, and so on. So our general solution then, u of x comma t, we could write this as the sum from n is equal to 1 to infinity of sine of n times pi times x times c sub n times cosine of 2n pi t plus d sub n of sine times sine 2n pi t. And so, based upon that, we need to now utilize this condition here. The thing though is we first need to take our partial derivative. So let me move this down so we can actually have room to accomplish this. The partial derivative, so u sub t of x comma t. We're taking the partial derivative with respect to t of this general solution that we just found. So this is going to be the sum from n is equal to 1 to infinity of sine of n pi x. This would be times negative 2n pi times c sub n times sine of 2n pi t plus 2n pi d sub n times cosine of 2n pi t. So when we use the very first condition up here first, this would be u of x comma 0. That is, of course, equal to x times 1 minus x from our equation above. And utilizing the summation notation, we have this is equal to n. The sum from n is equal to 1 to infinity of c sub n times sine of n pi x. And this is where x is between 0 and 1 inclusive. Now, based upon that then, we could then, and I need more room to do this, use that partial derivative that we just found. So this would be u sub t of x comma t. Well, I should probably replace that t with a 0, actually. This is going to be equal to cosine of x. And that is equal to the sum, this being from n is equal to 1 up to infinity, of 2n pi times d sub n times sine of n pi x. And this is where x is again between 0 and 1, inclusive. So, because of this, based upon those Fourier series, so let me write that. Because of these Fourier series, we could write that the sum as n is equal to 1 to infinity of b sub n times sine of n pi x, that is going to be equal to the sum as n is equal to 1 to infinity of c sub n times sine of n pi x. And because of this, we could write a couple of things. So b sub n, this is going to be equal to 2 times the integral between 0 and 1 of cosine of x times sine of n pi x dx. And this is what n is 1, 2, 3, and so on. Based upon that, we also have c sub n. And that's going to be equal to 2 times the integral between 0 and 1 of x times 1 minus x times sine of n pi x dx. And again, n is other numbers 1, 2, 3, and so on. And then finally, for 2 pi x, excuse me, I should be using an x there. 2n pi times d sub n. This is equal to 2 times the integral between 0 and 1 of cosine of x times sine of n pi x dx. Again, n is 1, 2, 3, and so on. But based upon that, we could write a final solution then of u of x comma t. This is going to be equal to the sum from n is equal to 1 to infinity of sine of n pi x times c sub n times cosine of 2 n pi times t plus d sub n times sine of 2 n pi times t. And as we found, c sub n is simply 2 times the integral between 0 and 1 of x times 1 minus x times sine of n pi x dx. And d sub n is equal to 1 over n times pi times the integral between 0 and 1 of cosine of x times sine of n pi x dx. And both of these are where n is equal to 1, 2, 3, and so on. And then look out for the next video based on the Laplace equation. Thank you.